Hello and welcome back. This video will be on section 6.4, and this is again looking at distributions of sample means. So I just want to go through sort of a scenario that we'll be looking at. So if we collect just a random sample from some population, the values in that sample will be distributed like the populations. So for instance, if we had some sort of population that had a couple of peaks, we had a lot of values down here and a lot of values down here. If you were to go out and randomly collect, say, a sample of size 100, you would expect, you'll get a few people at this peak, we'll get a few data values around this other peak, and it should be roughly distributed like the original sample. However, maybe we're only interested in the average of our sample. So we take an average, and then we go out and collect another sample, and we take the average value of this sample, and we continue doing this again and again and again. Well, this population will have an average, so we would expect that our sample averages, our sample means, should be close to the population mean. And moreover, if we keep doing this, we should continue to get values that are close to the population mean, and very rarely getting some values that are more to one side or the other. That sounds like a normal distribution. If we collect lots of large samples, and I'll define what this means in a second, the sample means are going to be normally distributed. So even though each individual sample will be distributed like the population, if I record lots of means of lots of different samples, we will expect that they form a normal distribution. Now, what do I mean by large? Well, usually 30. So as long as you're collecting samples with at least 30 individual data values, it's usually enough. Sometimes the population can be distributed in such a bizarre way that you need to collect over 30, but often 30 is going to be good enough. And while each sample is going to be distributed like the population, and then we have to look at lots of sample means to see a normal distribution pop out, if the population was already normally distributed, then everything is already fine. So if the population is normally distributed in the first place, it doesn't matter how big of samples you take. You could take samples of size less than 30, and their means will still be normally distributed. So it's only when the population isn't normally distributed that we really have to worry about taking large enough samples. And to say this a little bit more precisely, we have what's called the central limit theorem. And to summarize this before I read this, sample means are normally distributed provided we're taking samples that are large enough. This is all this says, but it gives us a little bit more information. For samples of size and greater than 30, the sampling distribution of the sample means is normally distributed, and not only is it normally distributed, we can describe the normal distribution. It has a mean of mu, which is the same as the population mean, which is the power behind this. We can use our sample means to estimate the population mean, and moreover, we know how they're distributed. They're distributed normally with a standard deviation of the population's standard deviation divided by the square root of n. So using this, we can calculate probabilities. So let's look at just like a scenario described in very vague terms. So we have a population. The population has a mean and a standard deviation. The mean tells us about where the center of the data is in some way. Standard deviation tells us how spread apart the data are. And then we're going to be taking random samples from the population Each random sample will need to have the same size. And then for each one, we can record X bar, which is going to be that sample's mean. So what can we say? If the population is normally distributed, so the original population is normally distributed, or as long as we're taking samples that are big enough, the average sample mean, as in the mean of all the sample means, is going to be equal to the population mean. The standard deviation of all of the sample means is the same as the standard deviation of the population divided by the square root of n, our sample size. And that means that we can find a z-score of the sample mean. And the z-score will tell us, is the sample mean unusual, or is it going to be fairly common? So let's look at an example using numbers. So we've got IQs are normally distributed with a mean of 100. So mu is equal to 100, and a standard deviation of 15. So sigma is 15. So then there's a couple of questions here. The first one, we've answered questions like this already. What is the probability of an individual having an IQ greater than 115? Okay, we can calculate the z-score, find this probability. The next question, what is the probability that a random sample of 9 individuals has a mean of greater than 115? So now we're not only looking at just one person having an IQ greater than this. We want to know what's the probability that 9 people have a mean of an IQ of above 115. And then what's the probability of even having more people having a sample of size 64 have a mean of greater than 115. So we would expect that, because 115 is a little bit higher than the mean IQ, that the probability that one person has an IQ greater than this, okay, we can calculate this. It'll be a small number, but it doesn't seem unlikely. The probability that 9 people have an average of over 115, that's more unlikely, because on average, people should have a mean of closer to 100. And if we take 64 people and take their mean IQ, their average IQ, it should be even closer to 100. So the likelihood that it's above 115 should be even smaller. Let's go through and actually calculate these. So for the first one, the probability that an individual has an IQ greater than 115. So what we need to do is we need to turn 115 into a z-score. So we know that the mean is 115. The standard deviation here is going to be, the mean was 100. Standard deviation was 15. So our z-score for 115 is going to be 115 minus the mean. And we're going to see how many standard deviations we are away. So this is going to be 15 divided by 15. The z-score is exactly 1. So we will go over to StatCrunch. And when we go to statistics, we have a calculator, and we have the normal distribution calculator. And we want to know, what is the probability that someone has an IQ greater than 1 standard deviation above. So again, this is going to be the z-score of 1, and if we draw a picture, we've got our normal distribution. Here's 0, here's 1. We want to know the probability that we're greater than 1, so we're to the right here. So I need to flip this over, so we're going to the right, and this should be 1. So the probability having an IQ greater than 115, bigger than 1 standard deviation away, is going to be about 15.87. So let's round that off. So probability is going to be equal to 0.1587. Cool. so this is our answer to the first question. For the second question, we're looking at a random sample of 9 individuals, and we want their mean IQ to be greater than 115. So we're going to have to adjust things a little bit. First of all, the mean of the sample means is still going to be 100, because even for samples, the mean of the samples is still going to be about 100. And the sample standard deviation is going to be the original standard deviation divided by the size of n, or sorry, by the size of our sample, which is going to be 15 divided by the square root of 9, because we're taking the mean of 9 people. Square root of 9 is 3. We're going to have a standard deviation of 5. Now, one thing that you'll notice is that here, our sample size is only 9. So maybe 9 isn't big enough. Do we have to have a sample size 30? No. Because IQs are already normally distributed. The only time we need samples that are big are when our data are not normally distributed. So we can have small samples here. So here's our sample mean standard deviation. So our z-score is going to be our mean, our sample mean minus the global mean divided by, let me just write the formula down, it'll be easier. So x bar minus mu over sigma divided by the square root of n. So this is going to be 115 minus 100 over 15 divided by the square root of 9. So this is 15 divided by 5. So this is 3. So now we have a z-score of 3. And again, we have our normal distribution. We want to know, okay, over here maybe this is 3. So we want to know what's the area to the right of here. So again, with our normal distribution calculator, we want to know what's greater than a z-score of 3. That's quite low. It's less than 1%, 0.0013. So this probability is going to be 0.0013. So the probability of getting one person whose IQ is greater than 115 is about 15%. Probability of getting 9 people and having their average IQ greater than 115 is now less than 1%. So we can see that wanting a sample to have a large mean is less likely than just getting one person. And if we continue, if we're looking at samples of size 64 now in this last one, again the average should still be 100, but now the standard deviation of all the sample means is going to be even smaller. So so the original standard deviation was 15. So this is 15 divided by the square root of 64 is 8. So this is going to be about 2. So a little bit less than 2. So when we look at our z-score, again we'll have our sample mean minus the population mean divided by our standard deviation, our new standard deviation, which is this. So we'll have 115 minus 100 over 15 divided by the square root of 64. And if we do this out, we get that this is going to be 8. So now we have a z-score of 8. and we're looking at the probability that something is greater than 8. 1 followed by 16 zeros.